All right, now we're getting into displacements of statically determinate beams and frames. By the end of this lecture series, you should be able to describe the deflected shape associated with different joints or supports, talk about elastic beam theory, determine the elastic curve or the deflected shape using the double integration method, and determine and use the principle of virtual work to determine a displacement or a rotation to a beam or frame. Double integration and virtual work are two different approaches to determining deflections and rotations. So we're going to talk about both of them. You can use either of them. They're just tools in your box, right? So, but first we're going to start off with just talking about deflections in general. And what is a deflection diagram, right? It's basically the deflected shape, right? It represents the elastic curve of the deflected shape at the center line. And always keep in mind that it is at the center line. The center line of a member, and we're talking about beam column. All right, something that can usually bend or, has, yeah. Okay. Now I'm going to go to a different file because it looks better this way. So let's talk about let's remind ourselves about what the different supports mean, right? If we have a roller, what displacement does it constrain, right? If it's this, if y is up, right? If we have x and y, then we're talking about my deflection in the y direction is 0 at my roller. It's generally providing some sort of reaction in the y direction. So if I were to apply a load to a beam that was supported by a roller, it would have the deflected shape like that, right? It could potentially deflect in the x direction, but it won't deflect in the y direction, in the vertical direction. And so we know that while the deflection at y is going to be 0, a roller allows some type of rotation at the support. Now let's look at a pin. What displacements or rotations does it constrain? You can't move horizontally and you can't move vertically. And if it was 3D, you couldn't move in or out of the page, right? It holds steady all deflections. So if I were to apply the same load to something with a pin, it would have a deflected shape like that. It's not moving in the X or Y direction. But it is allowing some type of rotation. What about if we have a fixed connection? What does a fixed connection keep constant? What does it constrain? You can't displace horizontally, you can't displace vertically, and now you can't even rotate. It's rotation about the Z direction, which is in and out of the page. Go back over here. If I apply a concentrated force, my deflected shape, well, I'm not allowed to rotate, so a cantilever would look kind of like that, right? There's no rotation, whereas a pin or a roller lets you have rotation at the support. The fixed support does not. So right here, right, this is flat. Horizontal. Reminding ourselves about frames. If we have a pinned joint, that means if I have two different members, right, my column being member 1 and my beam being member 2, at the joint, my deflection in the horizontal direction for member 1 is equal to my deflection at the in the horizontal direction for number 2. This is called compatibility. At that joint, the deflections have to be equal to the same. There's no difference. Similarly, in Y, my horizontal or my vertical deflection would be equal to my vertical deflection in the beam. My vertical deflection in the column is equal to my vertical deflection in the beam. However, this is a hinge, right? It's a pin, so it's allowed to rotate. It may start out as 90 degrees connecting, but maybe the beam rotates a little bit more than the pin. So my deflection or my rotation is not necessarily equal coming from both sides. Right? Like I said, this is called compatibility. Let's say I apply that load, that vertical load, somewhere on this beam. And now I'm going to rotate, have a deflected shape, and maybe my column only looks like that. So I've got some type of deflection, right, in the horizontal direction. That's the same if there's a little bit of a deflection right there. Maybe it goes down, Here, let's see. Maybe I could draw that a little bit differently. Right? The whole thing has some type of delta x, some small delta y, but notice it still stays connected, right? The pin means they're connected. However, compared to the horizontal, I have a rotation here and a rotation here, and those are not necessarily equal. So at a pin joint, the joint stays connected, but the members can rotate respective or relative to each other, right? It's like a hinge on your door, right? My door is still attached to the wall, but it's rotating if I apply a load to it, right, to shut the door. Finally, what if I have a moment frame? Well, a moment frame, if you recall, transfers a fixed joint, transfers all forces and all moments, whereas a pinned joint only transferred forces, which is why there was no compatibility with the rotations. A fixed joint transfers moment as well. So again, if I have member 1 as my column and 2 as my beam at my joint, the deflection in the horizontal direction of the column is equal to the deflection in the horizontal direction of the beam. My deflection in the vertical direction is equal to my deflection in the vertical direction for both the beam and the column. And finally, they're going to rotate the same. What do I mean by rotate the same? Well, if this is my beam and my column, they start out at 90 degrees. If I apply some type of load, they're going to deflect, but maintain that 90 degrees. Let's see. We'll do it again, right? We'll have some type of deflection, but this remains a 90-degree angle, even if it almost doesn't look like it. It should be. I'm going to have, I'm going to have some type of horizontal deflection, some type of vertical deflection, that's an X, some type of vertical deflection, dy, and the whole joint is going to rotate, but they're going to be the same values. So a fixed joint stays connected, but it prohibits relative rotation between the members. relative rotation. If it begins 90, it stays 90. Maybe it's not quite 90. I don't know why it would be a different angle, but right. Whatever it started out, it's going to stay that way. Okay. So we did all this work on moment diagrams, talking about bending. Let's hope we remember what positive and negative bending mean. What does that mean for the deflected shape? I've kind of talked about it a couple times, right? Positive bending is happy, it makes a smile. Negative bending is the other way. Let's say I have a beam a simply supported beam subjected to two equal and opposite forces, and they're on the same distance from the supports. What would my deflected shape look like? Probably look something like that. Like a little S curve. What does my moment diagram look like? Think about it. This reaction is probably, I don't know, I'm not going to do that. Well, moment at 0 right here, right? 0 right here. Probably going to be 0 right in the middle, because I switch from from negative bending to positive bending, right? If you do the math, it would look something like that. I have, oh my gosh, I just drew that backwards. I was all excited. Like something like that. You would think with my notes in front of me that I would look at them, but I don't. All right. This is positive bending. See, it makes a little smile. Positive bending, compression on the bottom. Kind of an evil looking little guy. All right. He's happy. This person, they're not so happy. They're sad. So we have let's write some notes, right? Positive bending. Concave up. Compression in the top of the beam. Tension in the bottom. negative bending, concave down, now we have compression in the bottom of the beam, and tension in the top. All right, if we look at our compression shape, right? If this was an actual cross section, we would have compression in the bottom of the beam and tension in the top of the beam. It looks like Pepe Le Pew or something. I don't know. Some French dude. And the point where it changes, that's where my moment equals 0, where I switch from positive to negative bending, and it that's called my point of inflection. So where I switch from negative to positive or positive to negative bending, I'm going to have a point of inflection. I'm going to have a moment that is equal to 0, and right. The slope right here is equal. Alright, what would this shear diagram look like? It probably look like, see, this is negative, so let's see if I had my shear negative, positive, something, I don't know. Yeah, something like that. Because here I have my maximum. Yeah. Get rid of that. Okay. So that's just talking about the point of inflection. Thinking about what the deflected shape might look like. I'm going to go back to my other file. So let's look at some other deflected shapes. All right. If you were in class, I might ask for a volunteer to come draw these, you know. So think about it. I'm going to give you like 2 minutes. Draw what you think they would look like, okay? This is a hinge over here. I haven't done too much with hinges. That's a hinge. Okay, it's been about 2 minutes. So let's look at this first one. I have this load right here, so I'd probably going down. As a result, that's probably going up, but it has to come back down because I got that roller or that pin right there. And this is a little cantilever, so it's just along for the ride, right? So I've got a curve, right? I've got what? Positive bending right there, and then some negative bending. So I've got a point of inflection where I change, probably right where that roller is, right? Point of inflection. Fine, I'll write the whole word out. Look at this one down here. So I've got this little cantilever, so it's probably going down. And then it doesn't necessarily have to come back. It's probably something like that. Yeah, that's terrible, right? This whole thing, there might be a point of inflection somewhere in there. All right, this is all negative bending. Oh no, there isn't a point of inflection. All right, it all just kind of goes for a ride. So this whole thing is a negative bending, right? We can say negative bending. Oh, no, I'm sorry. This one up here. Positive bending. Negative. This whole thing is a negative. It kind of makes a little U, upside down U. So let's look at the one with two fixed ends, right? Got our thing. Probably pushing it down, so I'm probably deflecting. But I got a fixed end here, so I gotta stay like that. So it's kind of hard to tell, but there's probably some sort of change in curvature there. And then this one similarly is going to come up, but it's got to eventually go back to being fixed right there with zero slope, right? I've got zero slope on this side and zero slope on that side. So I've got some type of change, right? This is probably a point of curvature, and then this, probably a point of curvature right here, and a point of curvature right there, right? I've got concave down. I don't know, maybe concave up, concave down, and concave up. So let's see, this is positive bending if it's concave up, negative bending if it's concave down, negative bending, and then positive bending. And I've got where it changes, a point of inflection, point of inflection, point of inflection. Finally, my last one, let's see. Got this load, so it probably wants to go down, but it's got to stay. So we got the same situation as above. This is a hinge. Which means it just has to rotate. And then probably just meet up with it, right? So I've probably got some negative bending here till about there, I don't know, somewhere. Some positive bending, and this is probably positive bending too. With that hinge force, I'm not transferring any moment, so they can rotate it relative to each other. Let's do another point of inflection right there. So that is looking at some beams. Now let's look at some frames. Okay. Here I'm just keeping with moment frames. So these are 90 degrees and they're going to stay 90 degrees. If I apply a vertical load or horizontal load up here, see these are fixed. So the whole thing's probably going to go like that. And then it's got to stay 90, but it's going to look kind of like that. I don't know if that is a good picture or not. Gotta come back is the thing. So this one's 90, this one's 90. Right? Probably gonna have, right? Happy, sad. Probably right in the middle. It's gonna have some sort of point of inflection. Where it's got to come back because it's got to stay 90 degrees. Now if I have a vertical in the load in the middle of my beam, this is just to highlight the difference between a fixed and a pin, right? This is probably going to want to deflect. and this is going to stay, but this one because it's a pin, it can rotate, right? This one has to stay fixed. My connections up here have to stay 90. But here, my column can start to rotate a bit, which is why the more that bows out, you're going to have some buckling, which is why you got to put a braced frame in there, not a moment frame, or not a pin connection with a moment, not a pin base with a moment connection. Okay, so that's just a little thought on our deflected shapes and remembering our compatibility and maybe what the deflected shape would look like based off of the type of supports that's holding the frame or the beam up. Okay, I'm going to stop right there and then we'll move on to elastic beam theory.